engineering problem. So before discussing this, we shall discuss what is differential equation of higher order. So a differential equation of the form f of x y dy upon dx d2y upon dx square, in this way dny upon dx raised to n is equal to 0, in which the dependent variable y and its derivative are present in first order and are not multiplied together, is known as differential equation of first order. So when this differential equation, when the order of the differential equation becomes more than 1, it becomes nth order. So in this topic we shall solve differential equation of nth order. Now we shall discuss what is linear differential equation of nth order with constant coefficient. So if a differential equation contains coefficient which are purely constant, as seen in this definition, k0 d raised to n y upon dx raised to n plus k1 dn minus 1 y upon dx raised to n minus 1 so on, plus kn y is equal to f of x. Here k0, k1, kn, they are purely constant. They cannot be the function of x. Such type of differential equation are known as linear differential equation with constant coefficient. So we shall solve this. फर्स्ट ऑर्डर फर्स्ट डिग्री का इसमें फंडामेंटल नॉलेज लगेगा, तो you see what is the procedure. Now solving linear differential equation with constant coefficient will require two parts. One is CF, another is PI. What is CF? CF is nothing but when right hand side of the differential equation is equated to 0, we get a general solution, and that solution is known as CF. And there is another solution, particular integral. It is a solution which does not contain any arbitrary constant. Means we shall find the solution with no arbitrary constant. Adding CF and PI will give us general solution. So in this we shall discuss first complementary function, method of solving complementary function. So here you see, consider the equation f of d operator y is equal to f of x. So we will solve CF. First of all, put f of x is equal to 0 and then find the polynomial equation of left hand side and find the root. So now when right hand side f of x is equated to 0, then we get k0 m raised to n plus k1 m raised to n minus 1 and so on. So now you see it is polynomial in m. So we will find the roots of this polynomial equation. We will find the roots of this polynomial equation. So we shall find the roots of left hand side. How will you find the root? As you did in your lower classes. If roots of this equation are real and distinct, say we have m roots, m1, m2, in this way we have n root, then complementary function will be of type c1 e raised to m1x plus c2 e raised to m2x, and in this way last cn e raised to mnx. Adding all these will give us complete solution, which will be known as complementary function. So this complementary function will be separate if roots are real and equal. When roots are real and equal, complementary function if roots are real and equal, suppose m1 is equal to m2 is equal to mk. If we have k number of roots equal, then the solution will be c1 plus c2x plus c3x square in this way. So we will multiply by this constant with x in increasing power, and we will get its solution. When roots are real and complex, when roots are real and complex, so when roots are imaginary, suppose we have alpha plus I beta and alpha minus I beta, imaginary root, we know that imaginary root always occur in conjugate pair. So corresponding to one pair of imaginary root, we have solution e raised to alpha x c1 cos beta x plus c2 sin beta x. So when roots are imaginary, suppose we have alpha plus I beta and alpha minus I beta be a pair of roots, then solution corresponding this root will be e raised to alpha x into c1 cos beta x plus c2 sin beta x. So beta is nothing but imaginary part, alpha is nothing but real part. So this is the root corresponding to one pair of complex root. For other root, if roots are real, we will put C3 e raised to m3x and so on. If two pairs of imaginary roots are equal, then we will follow step 2 method again. How we will put this? It is given in, it is given here. We will write e raised to alpha x. So here e raised to alpha x whole into c1 plus c2x into cos beta x plus c3 plus c4x into sin beta x. This is the solution corresponding to repeated imaginary root and so on. So you will get this through example very clearly. Now we shall study examples on this. Suppose we have d2y upon dx square minus 8 dy upon dx plus 15y is equal to 0. So right hand side is already 0. The whole solution which we will get will comprise of CF. So you see here equating symbolic operator. Symbolic operator means d upon dx is d. So here d2 minus 8d plus 15 whole multiplied by y is equal to 0. So this is the equation in terms of symbolic operator. Now equating the coefficient of y to 0, we will get auxiliary equation. Auxiliary equation means helping equation. You can also put d is equal to m for simplicity. So this equation will become m square minus 8m plus 15 is equal to 0. Now find the root as we were doing in lower classes. We have studied in 8th and 9th class how to find roots of polynomial. So here factorizing this, we have one factor m minus 3 into m minus 5 is equal to 0. So our roots are 3 and 5. These two roots are real and distinct. So we will follow the pattern of distinct root to find CF. So then our CF will be C1 e raised to 3x plus C2 e raised to 5x. A number of constant will always be equal to order. Since the order of this differential equation is 2, therefore number of constant will be C1 and C2. So this is your PI. Now similarly, when we go ahead, next we will discuss next question you see in example 5. we have d raised to 4y upon dx raised to 4 minus 2d2y upon dx square plus y is equal to 0. So as we did earlier, we will convert this into symbolic operator form. Means in place of d upon dx, we will substitute capital D. Then this equation becomes d raised to 4 minus 2d square plus 1 multiplied by y is equal to 0. From this, we will find auxiliary equation by equating coefficient of y to 0 and putting d is equal to m. So this is the equation, m raised to 4 minus 2m square plus 1 equals to 0. Now same thing, we will find the roots here also. So here roots are m square minus 1 whole square is equal to 0. So roots are m is equal to minus 1, minus 1, 1, 1. Now you see here the roots are real but equal. So here minus 1 is repeated 2 times, again 1 is repeated 2 times. So accordingly we will find the CF for this repeated root. Now you see for C1 and C2, for you see here for C1 and C2, we will take this first minus 1. So the solution will be C1 plus C2x whole into e raised to minus x. And for these two roots repeated, C3 plus C4x whole into e raised to m1x. m1 is here 1 and here m1 is minus 1. So in this way, this is the case for real and repeated root. So similarly, going ahead, we can find CF for imaginary roots. Now you see in this example, example number 6, this is d3y upon dx cube minus 2dy upon dx plus 4y equals to 0. So same thing, first of all, we will convert this into symbolic operator equation. Symbolic operator means we will replace dy d upon dx. Then this resulting equation will be d q minus 2d plus 4 whole multiplied by y equals to 0. Now putting d is equal to m, this equation becomes mq minus 2m plus 4 equals to 0. We are converting this into a polynomial of m for simplicity. You can also find root in terms of d. So now here the roots are, when you will go and find the roots, you see here by heat and trial method, one of the factor is m plus 2. Dividing this whole equation by m plus 2, the another quadratic factor will be m square minus 2m plus 2 is equal to 0. So here roots are minus 2. This is real and distinct. Another m square minus 2m plus 2 will give quadratic factor, and this quadratic factor corresponds to root 1 plus minus I. So this is now complex. So here we will show you how we get solution corresponding to complex root. You see here for minus 2 corresponding to minus 2, we have C1 whole into e raised to minus 2x, and for complex root we have e raised to x C2 into cos x plus C3 into sin x. So this is the case. This is for this is corresponding to complex root. So for each pair of complex root, we have e raised to alpha x into C2 cos beta x plus C3 into sin beta x. Beta is here 1, alpha is 1. So this is the root, and therefore this is the equation. So I will show you with another example, example number 7. So here this question is d2 minus 2d plus 5 whole square operated upon y is equal to 0. Already in the equation we are having right hand side equal to 0. So the total solution will be of CF. Now as we did earlier, replace this d by m. so that we will get equation in terms of n, and then we can find roots easily. So proceeding as we did earlier, the roots of these equations are 1 plus minus 2i, another is 1 plus minus 2i, means two pair of complex roots are repeated. So we have to put CF in this case for repeated root. So here you see e raised to alpha x. This is the case for first these two root, and this is the case for second two roots. So we have c1 plus c2x into cos beta x, beta is here 2 or alpha is 1. Similarly, plus c3 plus c4x into sin 2x. अगर इसमें एक और रूट रिपीटेड होती तो इसी में हम आगे ऐड कर देते प्लस सी थ्री एक्स स्क्वायर, और यहां भी ऐड कर देते प्लस सी फाइव एक्स स्क्वायर. इन दिस वे वी कैन फाइंड solution for any number of repeated root. So these are the cases for finding complementary function. Now we will discuss things for PI. So having known CF, then we can go for PI. That will be discussed in next class. So thank you, student.